In this section, we're going to focus on integrals that result in inverse trig functions. And we've worked with these functions before when we were finding derivatives. So back in chapter 3, we had our inverse trig functions and we found their derivatives. And now we're going to work backwards where we have the derivatives and we're going to find the inverse trig functions. Now, if you see in this box here, the book only highlights 3 of the integrals. It highlights inverse sine, inverse tangent, and inverse secant. The book doesn't stress the other 3, and that is because all you need to do to find inverse cosine, negative in front of the integral du over the square root of a squared minus u squared, that will give me inverse cosine. Same thing goes for this one, number 2. If I put a negative in front of that integral, that's going to give me the same formula but with inverse cotangent. And if I put a negative in front of this integral, then that's going to result in inverse cosecant. So the integrals 1, 2, and 3 in this box, all you have to do is put negatives in front of them, and then you get the other 3 antiderivatives of the inverse trig functions. So just keep that in mind. Let's work through our first example. We have evaluate the definite integral from 1 to 1/2 of dx over 1 minus x squared. Now we're looking for, when we're looking at our integrals, we're looking for an integral that has a square root in the denominator of something squared minus something squared. So that's going to give me, let's look at our first example. It says evaluate the definite integral from 0 to 1/2 of dx over the square root of 1 minus x squared. Now if we look at the formulas above, we're looking for a formula that fits this structure. If we look at the integral that involves inverse sine, and we let a be 1 and u be x, we've got it. So I'm going to use the integral formula du over the square root of a squared minus u squared is equal to inverse sine of u over the absolute value of a plus our constant. So all we have to do is say let x be equal to 1 and u be equal to x, and we've got it. So we have the integral from 0 to 1/2 of dx over the square root of 1 minus x squared. Since a is 1 and u is x, when I use this formula, I'm going to make those substitutions. So I have inverse sine. Since u is x, I'm going to put this x over, and then the formula says use the absolute value of 1, and the absolute value of 1 is just 1, and then I'm going to evaluate that from 0 to 1/2. So I don't need to keep that 1 under there. I'm going to rewrite that as just inverse sine of x from 0 to 1/2. So now I'm going to evaluate this. I'm going to take the inverse sine of 1/2 minus the inverse sine of 0. Now remember, with the inverse sine function, we restrict the domain from minus pi over 2 to pi over 2. So we have to be careful and make sure that we're picking the correct values. When I do inverse sine of 1/2, I get pi over 6. And then inverse sine of 0 is 0. So my final answer is going to be, okay, we have another example of finding antiderivatives involving inverse trig functions. So we have the integral of dx over the square root of 4 minus 9x squared. So we need to look at our formulas and find the closest form that we can to this so that we can identify which of those formulas we need to use. And again, it looks like we're going to use the formula du over the square root of a squared minus u squared is equal to inverse sine of u over the absolute value of a plus c. That looks like the closest thing that we have to this. So if I want to identify what my a value is, I'm going to look over here and say, well, what's being squared to get 4? Well, that would have to be 2. So we're going to identify a as 2. And then I'm going to look to see, well, what's being squared to get 9x squared? So in order to figure that out, I know that if I take 3x and square it, that's going to give me 9x squared. So I know that u is going to have to be 3x. Now, since it's not just x being squared and it's 3x, we're going to have to think about the chain rule. So if I have u is equal to 3x, then du is equal to 3 dx. So I am going to divide both sides by 3, and I'm going to get that dx is equal to 1/3 du when I divide both sides by 3. So when I set this up, I'm going to have 1/3 du over 4 minus u squared, and then I take the square root. I can pull the 1/3 out in front if I want. And then I'm going to use our formula for inverse sine, and this is going to give me inverse sine of u over the absolute value of a, which is 2, plus my constant. And then I'm going to have to go back and resubstitute for x. So I have 1/3 inverse sine. Okay, next example, it says evaluate the definite integral from 0 to the square root of 3 over 2 of du over 1 minus u squared. Now, this matches the inverse sine formula. So again, we're going to use that same formula. So that formula is du over the square root of a squared minus u squared. That will give us the inverse sine of u over the absolute value of a plus our constant. Now, if I look at this, a is going to be 1, and u is u. So there really isn't a whole lot I have to do here. So I'm just going to take the antiderivative and get inverse sine of u over the absolute value of a, which is 1. And then I'm going to evaluate this from 0 to the square root of 3 over 2. Now I can rewrite this as just inverse sine of u from 0 to square root of 3 over 2. We don't really need that 1 under there. So I'm going to plug in the square root of 3 over 2 first. And I'm going to do minus inverse sine of 0. When I take the inverse sine of the square root of 3 over 2, that's going to give me pi over 3. And the inverse sine of 0 is just 0. So my final answer is going to be pi over 3. For this example, we're going to find an antiderivative involving the inverse tangent function. So when we compare this problem with the formulas stated up in that box at the beginning of the lesson, this integrand looks like the inverse tangent integrand. So we are going to use du over a squared plus u squared is equal to 1 over a times the inverse tangent of u over a plus my constant. So this will be the formula that we're going to use. So what's given to us is the indefinite integral 1 over 1 plus 4x squared dx. So when I look at this, a is going to be 1, and u is going to have to be 2x, so that when I square it, I get 4x squared. So when I take the derivative of u with respect to x, and I multiply both sides by dx, I'm going to get 2 dx. So to replace dx, I'm going to have to replace it with 1/2 du. So I have 1/2 in front, and I have 1 over 1 plus u squared du. Now when I use the formula, I'm going to have 1 over 1, because a is 1, which is 1, and then I'm going to have inverse tangent of u over 1, which is just u, and then I'm going to have plus c. Now, when I go back and resubstitute, I'm going to have 1/2 inverse tangent, and then when I take the u and plug it back in, I'm going to get inverse tangent of 2x plus my constant. When we find the antiderivative of 1 over 9 plus x squared dx, this again looks like the integrand formula for inverse tangent. So we're going to use the formula of du over a squared plus u squared is equal to 1 over a inverse tangent of u over a plus my constant. So the integrand that we have is 1 over 9 plus x squared dx. If you notice, my a would have to be 3, and my u would have to be x. Now, there's nothing additional in there like 2x or 2x squared or anything like that, so we don't have to worry about any u substitutions. So I can just directly plug this into our formula of 1 over a inverse tangent u over a plus our constant. So anywhere that I see a, I'm going to replace it with 3, and anywhere I see u, I'm going to replace it with x. So I have 1 over 3 inverse tangent of x over 3 plus my constant. And that will be my final answer. Last example for this section, we're going to find the definite integral of the square root of 3 over 3 to the square root of 3 of dx over 1 plus x squared. Now when we look at this, this to me looks like the formula for inverse tangent. So we're going to use du over a squared plus u squared is equal to 1 over a times inverse tangent of u over a plus our constant. Now, it doesn't look like we have any inner functions that we have to worry about doing any u substitutions. I can see that my a is going to be 1, and my value of u is going to be x. So I can just do a direct substitution here. So I'm going to find 1 over a, which is 1, times inverse tangent of u over a. Since u is x and a is 1, I'm going to get x over 1, which is x, and then plus our constant. And because this is a definite integral, I have to evaluate this from the square root of 3 over 3 to the square root of 3. So technically I don't need to put that in there since I know it's going to cancel out anyways, but you can leave it in if you want. So now we just have to evaluate this by plugging in the square root of 3 first. So I have inverse tangent of the square root of 3 minus inverse tangent of the square root of 3 over 3. Now, when I find the inverse tangent of square root of 3, that's going to be pi over 3. When I take the inverse tangent of square root of 3 over 3, that's pi over 6. So when I subtract those, that's going to give me pi over 6. So my final answer is going to be pi over 6.